Welcome to the deep dive, where we take your curiosity and really plunge into some fascinating subjects.
That's the plan.
Today, we're going back to a moment in physics that maybe doesn't get the headline treatment, but wow, its impact is huge.
Absolutely.
Picture this. Columbia University, a quiet lab, vacuum chamber humming. You've got this delicate beam of molecules shooting through, coils clicking, invisible fields doing their thing.
And then, out of all that complexity, this tiny, sharp signal.
Exactly. Before lasers, way before MRI scans, before anyone was even seriously talking quantum computing, this setup gave physics this completely new ability.
A superpower, you called it.
Yeah, superpower. We're diving deep into Isidor I. Rabi, maybe not a household name, but his work literally, and I mean literally, taught atomic spins how to speak. And we're going to unpack what that means and, why it genuinely shapes the world you're living in right now.
It's really remarkable when you think about it. He took something fundamentally tiny, invisible, the spin of an atom, and didn't just find it. He found a way to, poke it, control it, make it report back with unbelievable precision.
So this whole deep dive is about his method, molecular beam magnetic resonance.
That's the one. Molecular beam magnetic resonance. And we'll trace a direct line from that lab bench. Straight to the technology in your pocket, the medical scan saving lives, even the absolute bedrock of quantum computing research today.
So the mission is to show how this really abstract physics idea
Seemingly
became this practical, tunable thing that, kind of built the modern world's rhythm.
Precisely. A civilization built on its beat.
Okay, let's get into it. Spin. Some of us might remember Gerlach, 1922, showed spin was real.
Right. The experiment that split that beam of silver atoms proved these little quantum magnets existed.
Yeah, but knowing something exists, that's one thing. Measuring it, figuring out its frequency, its magnetic strength, its internal details.
Especially when it's constantly moving, doing its quantum thing.
It just sounds impossible, like trying to catch smoke, basically.
That really was the core challenge. How do you measure something that's not just subatomic, but it's precessing, wobbling like a tiny gyroscope, and quantized, meaning it can only be in certain states? It's like hearing a whisper from across a crowded, noisy room while the person whispering is also spinning around.
Okay, that's a good analogy.
Rabi's genius was finding a way to make all those tiny, chaotic whispers line up.
Yeah.
To make them coherent, reportable.
Turning the whisper into something clear.
Exactly. Giving us a direct line into that quantum world.
So, if the quantum world was whispering these secrets, what was Rabi's answer? How did he give physics this superpower, get those spins to talk?
His answer, developed right there at Columbia, roughly 1937 to 41, was just brilliant. It's the molecular beam magnetic resonance method.
Okay, break that down.
Imagine it like this. First, you create this very fine spray of atoms or molecules, the beam.
Right.
You send it through some specially designed magnets. These aren't uniform magnets. Their fields vary in a specific way.
And these act like a filter.
Sort of, yeah. They polarize the beam. Basically, they nudge the spins, so they're mostly pointing in a specific direction.
They align them.
Got it. So they're all lined up. Then what?
Then comes the magic ingredient. You hit them with a weak, oscillating magnetic field. It's actually just a radio wave, a radio frequency, or RF field.
And not just any radio wave, right? You said it has to be just right.
Exactly. You carefully tune the frequency of that radio wave. You sweep it. And at one very specific, very precise frequency, bang.
What happens?
The spins flip. They transition to another allowed spin state.
And that flip changes things.
It changes how those molecules behave when they pass through a second set of magnets further down the line. The beam deflects differently. You detect that change, maybe the beam intensity drops at the detector.
So you see a dip.
You see a dip, and when you see that dip, you know you've hit the sweet spot. You've tuned into the spin's natural station. That's a resonant frequency. That's incredible. So it sounds like some really clever engineering was involved too, not just the theory. You mentioned a rotating field method and Larmor frequency. Help me out here.
Sure. So the Larmor frequency, think about a spinning top in gravity. As it spins, its axis also wobbles around, right?
Yeah, it precesses.
That wobble rate, that's its precession frequency. Spins do the same thing in a magnetic field. They precess at a very specific rate called the Larmor frequency. It depends on the spin and the strength of the field.
Okay.
Now, Rabi realized that the best way to flip these precessing skins wasn't just to shove them with a static field. It was to use an RF field that was oscillating or even better, rotating, at a frequency very close to that Larmor frequency.
Like pushing a kid on a swing.
Exactly like pushing a swing.
Hmm.
You push at the right rhythm, you build up energy smoothly. Push randomly, you just mess it up.
Go.
The rotating field, seen from the spin's own wobbling perspective, looks almost stationary, letting it gently tip the spin over.
So that perfect rhythm, that's the Rabi resonance, that dip we talked about.
Yeah. That's the resonance, yes. The exact frequency match needed for the flick.
And then there's the Rabi frequency, omega. That sounds like the speed of the flip.
You got it. Once you are at resonance, the Rabi frequency tells you how fast you're driving the spin back and forth between its up and down states.
Wow.
You can literally control how quickly the probability shifts from one state to the other. It's like watching water slosh back and forth in a bowl, and you control the sloshing rate with your RF signal strength.
So it's not just seeing it, it's controlling it.
That's the huge leap. It wasn't just passive observation anymore, it was active manipulation. And that rate, the Rabi frequency, became this fundamental new knob you could turn in the quantum world.
And why was that so profound? Being able to measure and control these tiny things with such precision, what did that unlock?
What it unlocked was incredible detail. By precisely measuring these resonant frequencies, scientists could suddenly extract things like the magnetic moments of nuclei, their intrinsic magnetic strength, and tiny energy differences within the atom, like hyperfine splittings, which come from the nucleus interacting with the electrons. Stuff that was purely theoretical, or very fuzzily measured before.
So spin went from this weird quantum idea.
Exactly, from an abstract concept
Yeah.
to metrology, a tool, a ruler, a way to precisely measure the invisible. It gave us this unprecedented high-resolution window into the heart of matter.
Okay, this is where it starts connecting dots for me for everyday life. Because this work, it didn't just stay in the physics lab.
Not at all.
It basically gave birth to some of the most transformative technologies we have. So what are the big ones? Where do we see Rabi's fingerprints today?
Well, connecting to that bigger picture, Rabi essentially gave us the handles for quantum coherence. He showed, find the rhythm, sync with it, and you gain control.
Right.
And that idea, that ability to control coherence, underpins almost all the coherent technologies that followed.
And the first big one, directly out of this, was NMR, right? Nuclear magnetic resonance. Chemistry students know this one.
Absolutely.
Yeah.
NMR is Rabi's method, but adapted. Scientists like Purcell and Bloch, who shared a Nobel for it later, realized you didn't need the molecular beam. You could just take a whole bunch of spins, often hydrogen nuclei in liquids or solids, stick them in a strong magnet, hit them with an RF pulse to tip them,
Like Rabi did.
and then just listen to the faint radio signals they emit as they wobble back as their coherence fades away.
And that signal is like a fingerprint.
A perfect fingerprint. Different chemical environments change the signal slightly. So NMR became this Rosetta Stone for chemists. Suddenly, they could figure out complex molecular structures.
Wow.
And for physicists studying materials, it became this amazing microscope to see how atoms were arranged and moving. It completely changed chemistry and materials science.
And then timekeeping. This just blows my mind. His student, Norman Ramsey, took it further. Ramsey fringes, atomic clocks.
Yes. Ramsey refined Rabi's technique. Instead of one long RF pulse, he used two short pulses with a gap in between where the spins just evolve freely.
Why do that?
It creates an interference pattern of the Ramsey fringes. And these fringes are incredibly sharp, much sharper than the single peak from Rabi's original method.
Sharper means more precise.
Way more precise. That sharpness lets you lock an electronic oscillator like the quartz crystal on a watch, but much better to an atomic transition with just absurd accuracy.
And that's the atomic clock.
That is the atomic clock. The definition of the second itself, that 9.192 gigahertz cesium frequency, is based directly on Ramsey's refinement of Rabi's resonance method. Your GPS, the internet, financial markets, they all rely on that stability.
Unbelievable. Then there's the hydrogen maser. Sounds like science fiction.
It kind of does.
Yeah.
It's basically like a laser, but using microwaves and the hydrogen hyperfine transition that Rabi's methods helped measure so precisely.
So it's amazing.
Exactly. It produces an incredibly pure, stable microwave frequency. These are vital as references for things like deep space navigation, talking to probes millions of miles away, and radio astronomy.
But for most people listening, the connection they'll recognize instantly is MRI, magnetic resonance imaging.
Oh, absolutely. Every single MRI scan is a direct descendant.
How does that work? Is it the same principle?
Fundamentally, yes. MRI listens mostly to the hydrogen spins in the water molecules inside your body. You line a strong magnetic field that aligns the spins.
Right.
Then the machine sends in RF pulses, Rabi pulses, essentially to tip those spins over.
Okay.
And then it listens. It detects the weak radio signals the spins emit as they relax back to alignment and lose their phase coherence with each other.
And different tissues relax differently.
Exactly. Bone, muscle, fat, tumors. They all have different water content in different environments, so their hydrogen spins relax at different rates. Those differences in relaxation times, T1 and T2, we'll get to those, create the contrast you see in the final image.
So it's mapping relaxation.
It's mapping coherence dynamics inside you. Tip, precess, relax, read. That's the MRI story built on Rabi's foundation.
And looking ahead, quantum computing, this feels like it comes full circle.
It really does. In the language of quantum computing today, those Rabi oscillations, the controlled flipping back and forth, that is how you perform operations on a qubit, the basic unit of quantum information. Rotating a qubit on its Bloch sphere representation is achieved by applying a precisely timed RF pulse, a Rabi pulse.
So every quantum gate?
Every fundamental single qubit gate that manipulates quantum information owes its existence to Rabi's pioneering work in coherent control. He wrote the first page of the quantum computing playbook.
Let's dive back into the physics just a bit more, make sure we grasped what's really going on when a spin speaks or resonates.
Okay, so at its heart, you have this magnetic moment. Think of it like a tiny spinning magnet. In a big static magnetic field, it doesn't just point straight, it precesses.
The wobble, the Larmor frequency?
Yeah, exactly. It wobbles at that Larmor rate. Now, here's the clever part. When you apply your weaker RF field sideways, and its frequency is near the Larmor frequency, from the spin's point of view, because it's already spinning around, that RF field looks almost stationary.
Right, the merry-go-round analogy.
Yeah. It's like you're on a merry-go-round, and someone next to you is spinning at almost the same speed. They look like they're barely moving relative to you. This slow-motion view allows the weak RF field to grab hold and smoothly tip the spin over.
And the probability of it being up or down starts oscillating.
At the Rabi frequency. That's the coherent exchange of energy driven by the resonant field.
So resonance isn't magic, it's just perfect timing, synchronization.
Yeah, that's a great way to put it. It's synchronization, matching the driving rhythm, the RF field, to the system's natural rhythm, the Larmor precession. That sync allows for this efficient, controllable, measurable energy transfer.
And if you're off resonance?
The lock weakens. The energy transfer is messy, inefficient. You don't get that nice, strong signal or that controlled flipping. It's like pushing the swing at the wrong moments. You just disrupt things.
But the real world isn't perfect. Spins don't just keep flipping forever. You mentioned T1 and T2, these relaxation times that are key for MRI contrast.
Right. Those are crucial. Real environments are noisy. Things bump into each other. So T1, that's called spin lattice relaxation. Think of it as the spin cooling down.
Cooling down.
Yeah, after you hit it with the RF pulse and tip it into a higher energy state. T1 is the time scale for it to give that energy back to its surroundings, the lattice, and relax back into alignment with the main magnetic field.
Okay, so T1 is about energy loss. What's T2?
T2 is spin-spin relaxation, or dephasing. Imagine all your spins starting out precessing nicely in sync like a perfectly choreographed dance troupe. But because they all experience slightly different local magnetic fields from their neighbors, they start to drift out of phase. Some speed up a tiny bit, some slow down. T2 is the time scale for how quickly they lose that synchronized rhythm, how fast the dance troupe falls apart.
And those times, T1 and T2, they tell you about the local environment.
They tell you everything about the local environment, how mobile molecules are, what kind of interactions are happening. And because different tissues have different T1s and T2s, MRI can distinguish them. That's where the diagnostic power comes from.
It really feels like Rabi didn't just invent a measurement technique. He changed how we even think about measurement in the quantum realm.
He absolutely did. He helped forge what we could call the metrology mindset, this core idea. If you could find a stable quantum loop, tune into its rhythm, and count its cycles, you can build incredibly precise standard. You can redefine fundamental units. It's the spirit behind lasers, atomic clocks, the modern redefinition of the kilogram, all of it. Rabi showed that time itself could be measured as the counted cycles of a perfectly synchronized quantum motion.
And his lab at Columbia, it became this engine for precision. You mentioned Shelter Island earlier.
Yes, the Shelter Island Conference in 1947 was a landmark. Physicists presented brand new, ultra-precise measurements like the Lamb shift, a tiny unexpected energy shift in hydrogen, and the electron's slightly off magnetic moment.
Measurements made possible by these new resonance methods.
Largely, yes, or inspired by that level of precision. And these results were shocking. They didn't fit the existing theory of quantum electrodynamics, QED. They forced theorists like Feynman, Schwinger, and Tominaga to develop the much more sophisticated version of QED we have today.
So the experiments drove the theory.
Absolutely. Rabi's methods provided the incredibly sharp data that pushed theory to its limits and beyond. That precision ultimately made the entire standard model of particle physics testable. You need that kind of accuracy to see the tiny effects predicted by the model.
So his blueprint was basically find the rhythm, drive it, detect the response, lock onto it.
That's a great summary. Prepare the system, drive it coherently, detect the result, and lock your instruments to that quantum answer. It turns out these coherent quantum loops are the universe's cleanest rulers. They simplify complexity down to a single, countable frequency.
And Rabi, the man, he wasn't just in the lab, right? He was building things, advocating for science.
Oh, definitely. He won the Nobel Prize in 1944 for the resonance method, of course. But he was also instrumental in founding Brookhaven National Lab after the war.
A major U.S. research center.
Right. And he was a key advisor in the discussions that led to the creation of CERN in Europe. He understood the need for big science, for collaboration. He just had this practical genius, always asking, okay, that's interesting, but how do we make it answer us? And then he'd figure out how to build the coils to do it.
And that legacy, those consequences, they're still unfolding all around us.
They really are, every day. In quantum control. Every time a physicist applies a precisely timed pi pulse to flip a qubit state, that's a Rabi pulse.
Right.
In quantum sensing. Atomic magnetometers measuring brainwaves, NV centers in diamond, detecting tiny magnetic fields. They're all reading shifts in quantum sync rates, building on his ideas.
Medical imaging.
Medical imaging keeps advancing. MRI techniques like diffusion tensor imaging, mapping nerve fibers, or fMRI, mapping brain activity, are just more sophisticated ways of listening to those T1 and T2 relaxation stories.
And navigation and timing.
Still fundamental.
Yeah.
Navigation and timing. GPS, deep space communication, synchronizing global networks, all impossible without the ultra-precise clocks born from Rabi's lineage.
So, as we wrap this up, what's the big takeaway? What did Rabi's deep dive into matter really give us?
I think the key is that Rabi didn't just study motion. He figured out how to build technology that lives off its rhythm. If you look at it through the lens of, say, motion theory, you see structure is stabilized motion. And measurement isn't passive. It's synchronized participation in that motion.
Okay.
Rabi took that philosophy and made it practical. He made it tunable, calibrated science. He proved, fundamentally, that if you can sync with a natural loop, even an invisible quantum one, you can measure it, you can steer it.
And you can build a civilization on its beat.
Exactly.
So the next time you check your phone relying on those atomic clock signals or you see an MRI image, just take a second. Remember, you're seeing the legacy of someone who taught the invisible world to speak.
And taught us how to listen.
Right. Which makes you wonder, what other hidden rhythms, what other fundamental loops are out there just waiting for us to figure out how to sync with them, waiting to be heard?